System of interconnected bodies refers to two or more bodies that are connected together and therefore moving together. We shall consider a 5 kilogram and a 3 kilogram mass at rest on a surface. The gravitational weight force on each, being 30 newtons for the 3 kilogram mass, 15 newtons for the 5 kilogram mass, are balanced by the normal reaction forces, as we have already seen, being 15 newtons for the 5 kilogram mass and 30 newtons for the 3 kilogram mass. As these forces are balanced, Newton's first law predicts that the bodies will remain stationary because they were initially stationary. We can now apply an external force, in this case 120 newtons acting to the right. Now this external force is only applied to the 3 kilogram mass. However, it will affect both masses as they are interconnected together. The whole situation becomes easier to see if we remove the weight and the normal reaction forces, as they will not influence their motion. As there is now a net force acting on the system, Newton's second law predicts that the body will accelerate. The acceleration can be found by applying the Newton's second law equation. Acceleration equals F net divided by mass. In this case, the F net acting on the system is 120 newtons, but the total mass of the system that is accelerated by the 120 newton force is 8 kilograms, not only 3. Therefore, the acceleration is 15 meters per second squared. That is, without considering friction. If the bodies are moving to the right, there will be frictional forces acting to the left. Let us consider that a frictional force of 10 newtons acts on the 3 kilogram mass to the left, and a frictional force of 30 newtons acts on the 5 kilogram mass. Considering friction, 120 newtons acts on the system to the right, but 10 newtons and 30 newtons in combination act on the system to the left. Both these are external forces. The net force therefore reduces. The net force is now 120 minus 30 minus 10, that is 80 newtons. The acceleration can again be found by using Newton's second law equation. In this case, the net force is 80 newtons, accelerating a total mass of 8 kilograms, and therefore the acceleration is now 10 meters per second squared. The two bodies in this case are interconnected by a link, and this link, while the body is in motion, is under tension. The tension force is one and the same, and it will act at an unknown tension of T1 to the left for the 3 kilogram mass, and an unknown tension of T1 to the right for the 5 kilogram mass. We need to be able to find the value of T1 under these conditions. T1, of course, is not an external force. It is called an internal force. It's a force acting between the bodies that are interconnected together. In order to find T1, we can do a Newton's second law analysis, looking at the forces acting on each individual body. Let us concentrate on the 5 kilogram mass. The forces acting on the 5 kilogram mass are T1, which is actually what is accelerating it to the right, and the frictional force, which is slowing it down to the left. Of course, we know that the body is already accelerating. We know that the acceleration of the system of both masses is 10 meters per second squared. And so we know that there will be a resultant force on the 5 kilogram mass, and therefore T1 must be greater than 30 newtons by an amount sufficient to accelerate it by 10 meters per second squared to the right. Applying Newton's second law in the form F net equals mass times acceleration to the 5 kilogram mass gives us a resultant force of 50 newtons. So the net force acting on the mass is 50 newtons, but the net force is also T1 minus 30. T1 is greater than 30 by an amount equal to 50 newtons. T1 minus 30 therefore equals 50 newtons. This makes T1 equal to 18 newtons. We have now found T1, the tension in the string interconnecting the bodies. The exercise will be very similar considering the 3 kilogram mass. Considering the 3 kilogram mass, the F net is 30 newtons. The mass is 3 kilograms. The acceleration we already know is 10 meters per second squared. That gives a resultant force of 30 newtons. Looking at the forces acting on the 3 kilogram mass, we have 120 newtons acting to the right, minus 10 newtons acting to the left, and the tension force also acts to the left. We can therefore say that the applied force, which is 120 newtons, minus the unknown tension force, minus 10 newtons frictional force, should equal the resultant or net force of 13 newtons. Since the applied force is 120 newtons, this makes the tension in the string, again, 18 newtons. That is no surprise. It is the same interconnection.